pretty much everyone who has done something very, very important in C++ is here at least every other year or so. Directly interfacing with those people is just an incredible boon to your career, especially early in your career. Getting to pick people's brains on things, just hanging out, talking with people, you can't put a price on that. And you don't get those online.
All right, it looks like we can go ahead and get started. So hello everyone. I'm Daniel. I realize I forgot to make a slide saying who I am, so I'll just tell you who I am. I'm a teaching professor at CMU. I teach algorithms classes to graduate and undergraduate students. And in my spare time, I like writing C++ libraries for parallelism and concurrency. So today we are going to be talking about parallel range algorithms. Not to be confused with another talk which is also about parallel range algorithms in just a couple hours. I only found that out on the slide. I'm seeing waving in the back. So we've got another one in just a couple hours. I don't actually know how similar or dissimilar the two talks are. So, maybe check out both, but hey, mine's first. So, if they are exactly the same, well, at least mine's first. So I got lucky on the schedule. Yeah, so we're going to talk about parallel range algorithms today and how to make them fast, okay? So what we're going to learn about, we're going to really start with the core of the problem, which is what is the brick wall for parallel algorithms? What causes them to stop scaling? Okay, something goes wrong, and we're going to figure out what that is, and then we're going to talk about laziness. Okay, laziness is going to be the cure to all of our problems that we're going to encounter. And then we'll talk about, well, why currently parallelism and ranges don't play super well together yet. Okay, so we can't quite implement our cure that we want, but we will talk about how to fix it. We will figure out an idea that will fix it and get us the best of both worlds. And then we'll go through some concrete algorithms. We'll talk about algorithms for our parallel lazy ranges. And finally, of course, I have to prove to you that, well, it actually works, that it actually makes things faster. So we'll do some applications and some benchmarks to show that it actually makes things faster. It actually solves the problem that we hypothesized was a problem. Okay? So really, to dive right into what is the problem? Well, scalability, right? So when you're writing parallel code, right, what you want is you use more cores and your code gets faster, right? That's kind of the idea, right? So I just went ahead and I benchmarked some simple parallel range algorithms, right? My implementations of them, not standard library ones. These are my implementations, but the performance would be pretty consistent with any implementation. These are very simple standard algorithms. So I have here some benchmarks for reduce, transform, scan, and filter. If you don't know what scan is, right? Scan is a fancy name for prefix sums, right? So you're just computing the sum of every prefix of your range, okay? A fancy term for that is a scan. So I have here a performance graph. So this is showing throughput, right? Because throughput graphs are better than runtime graphs, because if you plot runtime against cores, they go down and then you can't see the difference. Like, they don't look as good. So throughput is easier to see. Bigger means better, right? As opposed to runtime. Smaller means better. So you can see, okay, as we add more cores, I guess the performance, it goes up, but at the very beginning, it goes up a lot, right? Like at the very beginning, we're very happy. We're adding more cores, we're getting a lot more throughput. But very quickly, we start to hit a wall where we add more cores and we only get a little bit more throughput. And then we add more cores and we get barely any more throughput at all. So, the scaling here is not so good, right? And, I want to emphasize this is very important if you're working with, high performance computing and you're using lots of cores, right? If you're only going to use 4 cores, this is probably fine, right? You probably scale well into 4 cores and you are totally okay. So if you ever go to any talk on parallel algorithms, right, and they show you a scaling graph, but they stop at 8 cores, tell them to make the x-axis go more, right? Like you want to see what happens with a lot of cores, right? Like everyone has at least 8 cores these days. We want to really look at big multi-core systems, right? So We can see this even a little bit more clearer if instead of just plotting the raw throughput, we look at the actual parallel speedup, right? So the parallel speedup is just defined to be, right, like how much better is the throughput compared to that same algorithm with just one core, right? So this is just how much faster is it compared to when we didn't use multiple cores. So a perfect, an ideal parallel algorithm, right? It would be a straight line with gradient 1, right? Like twice as many cores, twice the throughput. 10 times more cores, 10 times more throughput. Now you can rarely get perfect, right? But we'd like to get close. But what you can see here is that we're not even close, right? We are very much not even close. At 70 cores here, 72 actually, we're still not even at a 30 times speed up here, right? We're only 20 something speed up in the best case. In the worst case, 15, 16 for 72 cores. That's not good value for money, right? You throw 72 cores at something and you get 15 times faster, right? You question whether you should have bought 72 cores. It doesn't seem like it's really doing its job. Okay, so something's going wrong. What's the bottleneck, right? We threw more cores at it. We got more cores, so we have more compute power. So what are some hypotheses here? What's going on? Well, compute operations? Well, no. I mean, these algorithms are, take my word for it, they're all work efficient, right? Work efficient is a fancy term that means, asymptotically they do the same amount of work as the sequential algorithm. So they're not like accidentally doing more compute when you add more cores. They are doing a good amount of work. Okay, so that's not the problem. Maybe my code's just not parallelizable enough, right? Like my parallelism is bad. Well, I claim again, no, these are good. Theoretically, these algorithms should scale well to thousands of cores. Like there is enough parallelism in the algorithm that they should keep scaling. Okay, so if you've been to, talks about performance, right? Especially C++ talks about performance, usually right now there's one word that people will start thinking of like, I know that other thing that causes performance problems that isn't just how much compute that I'm doing. What's the word every performance talk is going to tell you about? Someone shout out a word. Cache. Locks if you're doing concurrency, yes, but we're actually not doing any concurrency today. But yeah, cache, right? That is the word you think, cache. It's always the damn cache, right? Actually, not quite in this case, although it's close. This answer is close, but it's not quite right. These algorithms are all cache efficient, actually, right? Like they read left to right. They read everything that they put on the cache line. They're not just bouncing around random access. But we're close, right? I mean, cache is about memory. So we were really close. The answer is about memory, but it's not cache, it's actually main memory, the not cache memory. It's actually memory bandwidth to our DRAM, okay? So essentially, we are running out of memory bandwidth. Our algorithms are so fast, right? They're so efficient at computing that they can't actually read the memory fast enough. Like they read some memory, they compute the answer, and they say, cool, I need more memory. And they actually have to sit and wait. They're actually not getting memory reading fast enough to compute what they want to compute. So they're actually simply running out of memory bandwidth. They cannot read memory fast enough. Okay? And we have a sort of a term for this, right? Because this shows up all the time, right? So an algorithm like this is called memory bound or bandwidth bound or memory bandwidth bound, some combination of those words. If the primary bottleneck for its scalability is memory bandwidth. Okay, so you're just running out of memory bandwidth before you can actually utilize all your cores. So throwing more cores barely helps you because you don't have enough memory bandwidth to feed all the cores with data to do something with. Okay, and as a general rule of thumb, and again, this is a generalization, so someone's going to complain in the YouTube comments, but as a general rule of thumb, most simple data parallel algorithms are in this category, right? This is the most common thing that will bottleneck your parallel algorithms, right? If you're doing data parallel processing, this is 90% of the time gonna be the bottleneck for you, okay? So we can actually kind of verify this hypothesis, right? If you don't want to take my word for it, if you don't believe me, we can kind of verify this actually by looking at the numbers. We can look at our relative performance numbers. So I'm going to bring up this graph again, and we're going to talk about how much memory bandwidth these algorithms actually use. Okay, so here's the plot again, and we can think about how much bandwidth these algorithms actually use. So reduce, right? Reduce just sums up all of the numbers, right? So reduce here is the most efficient algorithm here because it does the fewest memory operations. It pretty much just needs to read all the elements in the input. It does negligibly few writes to input because the output's just one number. So this algorithm pretty much just does n-ish reads for an input range of size n and negligibly few writes. Transform, on the other hand, does about n reads and then n writes because it reads everything, applies the function, and writes out the answer. And it turns out that on most machines, probably almost all machines, at least on mine, right, writes tend to be slower than reads. So the bandwidth to do writes it takes more bandwidth to do writes than reads. So writes are slower. So we would expect then that transform should be like even worse than like twice as bad as reduce, because not only is it doing twice as many operations, n reads, n writes versus just n reads, those writes are slower. So if writes are about 70% slower, which is basically what we've measured on our machine, I don't know how this translates to other architectures, but this is an old like Xeon processor. So on this machine, we've measured it. Writes are about 70% slower than reads. So you would expect transform to be about 2.7 times worse than reduce. And if you look at the numbers, that's pretty much roughly what they show up as. Similarly, scan. So we'll talk about how scan is implemented in a bit, but for now, take my word for it. Scan in parallel takes about 2n reads. You actually have to go over the input twice, and then you write out the n answers. So you would expect this to be, 3.7-ish times slower than reduce. And if we just normalize our plot now, right? So instead of throughput, we kind of plot like normalized bandwidth. So we account for the fact that like how much bandwidth they're actually expected to use. They, within some, noise and random stuff going on, they pretty much line up. So this provides some evidence that bandwidth is in fact the dominating factor. Like it is what is causing all of these algorithms to sort of peak and flatten out, right? So this is some evidence that I'm not making that up, right? That the bandwidth is the factor here for these algorithms running out of scalability long before we run out of cores. Okay, so memory is the problem. So how do we attack this, right? How do we reduce the amount of memory that we need to use in our algorithms? And there is a technique for this, and generally, right, comes under a few names. We're going to talk about fusion and laziness, okay? These are the techniques we're going to try and look at to help us reduce memory consumption, right? Reduce memory bandwidth. So let's talk about composing sequence operations, because the effect of this it becomes even more pronounced when we're not just doing one, but doing many operations. So let's say I have a vector, right, with some data in it, and I have some temporary vectors, B, C, and D, where I'm going to store temporary stuff that I'm computing. And I'm going to compose a bunch of sequence operations. So here's my A. I'm going to do a transform, right? For every element, double it and add 1. So we transform the elements, we write them from A to B. And then I'm going to do a scan, because scan is cool, right? So that's going to compute the sum left to right, the prefix sums. We're going to write those into C. And then I'm going to filter the results, which is called copy if, rather than filter for some reason. So we're going to copy if. Makes sense, we are copying the elements. So we're going to copy from C to D for all the elements that are divisible by 3, right, that satisfy this predicate. Okay, so by composing these operations, like if I just do it like this, right, this doesn't look great, right? Each of these operations individually is going to compile into a loop. So this algorithm, right, if you can call it an algorithm, I just made it up, but this code does about 3n reads and writes to main memory, okay? That's a lot of reads and writes. So we would call this code extremely memory inefficient, right? It's doing 3 loops where it's like reading and writing basically the same stuff over and over again. So we have a technique for this though. It's a fancy name, it's called loop fusion, right? It sounds cool, right? And the idea, right, if we took the code on the previous slide and we hand wrote it, or we approximated what the standard library would, compile that into, we would expect that code to be, roughly the same as these loops, right? We're doing the transform, right, for each element in A, double it and add 1. Then we would do our scan, which is this, is just a prefix sum, right? You're keeping a running sum left to right and adding the next value at each iteration. And then the filter, aka copy if, right, again goes through the sequence C, and for each element, if it satisfies our predicate, right, if it's divisible by 3, in this case, we write it out to D, okay? So those 3 standard library algorithms on the previous slide would roughly morally do the same thing as these loops, which we can write by hand. But if you see these loops by hand, you may see, well, I don't think I need to do 3 separate loops here. I mean, they're kind of just reading something, writing it, and then in the next loop, reading it back and doing something else. We could actually combine these 3 loops into one. This is called loop fusion. If we do that, we might end up with code that looks something like this, right? Color-coded to see which loop is which. But essentially, right, that transform and that scan and then that filter, they don't have to happen one after the other. They can happen at the same time because they're each operating on like the same range, and they're operating in just the same order, left to right. And so now this code, instead of needing all those temporaries, just goes straight from the input and bam, it writes the output, right? Much better. So this fused version of the code, it only does like n reads and n writes instead of 3n. So this is like 3 times more memory efficient. Okay, great, we love that. But on the other hand, right, this is C++, we like using abstractions. We like using standard library algorithms. The moral of this talk isn't don't use standard library algorithms, they're slow, just hand write everything because, well, it's more typing for you and it's also, more complicated algorithmically to figure out how to write these, fused loops. It's even more complicated in parallel, right? We haven't even hit parallelism yet here, right? This is sequential. Manually fusing parallel stuff is very tricky. You can do it, but it's hard. So, we like having algorithms in our libraries that do the hard stuff for us. So we want to keep our abstractions, but still get this benefit here. And, what do you know? We got lucky a few years ago when C++20 introduced views. All right, so views in the C++ standard are essentially defined to be cheap to copy ranges. Okay? And essentially, they are forced by contract to evaluate things lazily because they are required by the standard to be constant time, constructible, copyable, even calling begin has to be constant time, which causes a nightmare there are other talks that talk about why that's a nightmare. Essentially, by contract, they are therefore forced to evaluate things lazily. They can't compute the answer and save it somewhere because that would not take constant time. They are forced to compute on the fly as you iterate, which also is really great for memory efficiency because it means that they don't have to write all these results to a temporary vector. They just compute on demand. So there's no wasted temporary space. So our previous algorithm could also be written something like this, right? Using the cool like overloaded pipe operator, right? For the view adapters. You don't have to use that. You can chain function calls, but this looks cooler. So we're going to do this. Right, our previous code is morally equivalent to this, right? We're doing a transform, double it and add 1. We're doing a scan where we add things, and then we are filtering out and keeping the the divisible by 3 elements. And the nice thing is, right, because these views get evaluated lazily, they are by contract not allowed to do linear work and store the results somewhere. These things fuse together automatically. And this code essentially does just n reads and writes instead of 3n once again. So big take-home message here is that essentially doing lazy evaluation and then composing things effectively gives you automatic fusion. Right? If everything's evaluated lazily, they can't, by definition, write out all their results to some intermediate storage. They have to go lazily and they therefore will fuse together. Okay, so it seems like we've found a tool. We found a tool to reduce memory consumption, right? Automatic fusion, lazy evaluation. This is how we're going to reduce memory bandwidth usage, right? We're no longer writing out things to intermediate arrays, okay? So 2 key messages so far then. Most simple parallel algorithms are memory bound and lazy evaluation, right? This gives us automatic fusion, and this reduces bandwidth consumption. So if you look at these 2 things side by side, you're like, well, we've done it, right? We have solved the problem. Let's just use lazy views for parallel algorithms and we've done it, right? That's it. That's the whole talk. No, I'm kidding. There's a lot more. It doesn't work. That's it. So unfortunately, it doesn't quite work out like that. So we have to sort of dig into how ranges work a little bit more under the hood. going to have to take a detour and look at range categories for a second. So if you look in the standard and you look at ranges and iterators have these categories which tell you like what you can do with them. So we have, at the top contiguous, right? This is not used very much, this is just everything is stored in contiguous memory like vector or array. The more important ones, right? Random access, right? Random access means in constant time I can look up any element in my range, okay? That's important. On the other hand, we have forward and bidirectional, where you cannot in constant time look up any element. You can only go like left to right or right to left, bidirectional, okay? You can't just jump into the middle of the range in constant time. You could go one way or the other. And now we have a bit of a problem because if I want parallelism, right? I need this. I need to be able to jump into lots of places within my range because if I can only go left to right one at a time, I can't parallelize anything, okay? So we kind of need random access for most parallel algorithms. On the other hand, if you're evaluating lazily, you don't have every value ready to go. You're computing one by one. So most lazy views produce these. So our parallel algorithms need random access or better, but our lazy views are only going to typically give us forward iterators or bidirectional. And we're not even going to mention input and output iterators because they're even weaker. They're not going to help us today. Okay, so it seems like we're in this bit of an incompatibility here, right? We want laziness and we want random access, but they're kind of incompatible, right? Because let's think of some examples. Think of a lazy scan, right? You're tracking your rolling sum as you go left to right. If I want to random access and say, all right, what's that one, right? What's the fifth one? Well, you don't know unless you've already done the sum of the previous elements. So either you've had to already iterate up to that point, or you've had to pre-compute it and save the answer. So that's not lazy. What about a filter, right? Kind of a similar issue. If I ask you, well, which element comes in that position in the filter, you need to know how many elements before that position got filtered out because your position, right, depends on, well, how many elements before you disappeared because you're going to move across that many. And for the same reason, right, you kind of can't do that both random access and lazy. You kind of get one or the other. So we're at this bit of an incompatibility here, right? We want to be able to jump into the middle of a sequence to do things in parallel, but we can't because for many of these ranges, the value or even whether an element is there or not depends on stuff that comes before, right? It depends on knowing what happened before, which means you either have to have iterated there or stored the answer. Okay, so here we are again with our iterator categories. So, well, what do we need? Well, random access is too stringent. We can't satisfy random access and still be lazy. But being forward or bidirectional is not good enough for parallelism. So we need a new one. We need a middle ground. We need something in the middle between the two, right? Something that is more powerful than forward so we can actually parallelize, split work across threads, but something that is weaker than random access so that it's not so stringent and impossible to be lazy. Okay, so what on earth does this middle ground look like? Well, we're going to just take inspiration from how parallel algorithms actually work. So we're going to do an example of how a parallel scan actually works and use that to inspire, like, okay, what do we need? Like, what does this algorithm need to be efficient? So the way that parallel scan and many parallel algorithms tend to work, of course, this is a quite general technique. Start by breaking our range into blocks. And now we can process all the blocks in parallel, right? So we can hit, one worker for each block, and they will sequentially process each block, and they'll compute the sums of the blocks. Okay? Now that we have our block sums, now we want to do prefix sums of those block sums, which itself, of course, is another scan. So, there are two ways about this. If the number of blocks is small, just do that sequentially. If there's a large number of blocks, you can recursively scan again, right, to compute those prefix sums. Now, once you have the prefix sums, and we're ready to write the answer, those prefix sums essentially tell us the starting value for each block. And now we can once again, in parallel for each block can then just sequentially fill in the sums, right? Going left to right, like so. So the idea, right, is split into blocks, process blocks in parallel, but then within each block, you're just doing something left to right, right? You're doing something entirely sequential. So we don't need like complete random access here, do we? Right? We're still processing blocks sequentially. So this is actually, quite a general pattern. Many parallel algorithms fall into this, this flavor, right? You do some local pass where you process all your blocks in parallel. You do some sequential computation on the block. There's then some kind of, global aggregation where you take the summaries per block and combine them, right? Like doing a prefix sum on the block sums in the case of scan. Then a second local pass to go through and use that global information to figure out the answer in each block, right? So we get this sort of, this picture here again. So this is a very nice technique, and it works for, not just scan, it works for lots of parallel algorithms. And the key idea here is that blocks are what matter, right? Blocks are the unit of parallelism here. We don't need to be able to parallelize over every element, right? I don't need random access to every single element. I just need blocks. Each block can be sequential, right? Left to right, as long as I can get my hands on a bunch of blocks in parallel. That's what we need. That's the interface we need. So we're going to define our new middle ground here. We're calling it a block iterable range. So a block iterable range is a forward range, but you get random access to the blocks. So you essentially get random access to a bunch of checkpoints in the range, and those checkpoints are the starts of the blocks. Okay, and that way you can parallelize over the blocks because you get random access to those blocks, but within each block, there's still forward ranges. So there's still room there to be lazy and not actually pre-compute everything up front, right? So essentially we're just extending, the range concept, right? A range is just something that has begin and end, which return iterators. We just also need to be able to say begin block, right? Give me the ith block. And for symmetry, we can also get the end of a block, but the end of a block is just the beginning of the next block. So really all we're adding is one extra thing. Give me a block, random access, and that's it, right? Everything else is still a forward range. Everything else is still forward iterators. And is this it? Is this enough? And I claim, yes, this is what we need. So why does this do what we want? Well, we have blocks that we can random access, which means threads can now work on separate blocks in parallel. So we have our parallelism. But because each block is just a forward range, we can be lazy, right? We don't have to know that whole forward range up front. We can compute it on demand just like we would with a sequential, right, stood ranges views algorithm. So we get this like best of both worlds here. And this turns out to be what we need for a lot of nice real life parallel algorithms on ranges. So not just scan, but many algorithms can fit this pattern here, right? Where you do some pass through your blocks, you do some global aggregate information, and you then propagate those back to the blocks, okay? And best yet, right, these are composable, right? As long as your blocks are the same size, which is just something we'll enforce, right, in our algorithms, you can compose them, which means they can fuse together. You get this nice pipeline where everything fuses together, just like in the sequential stood ranges views. And we get everything we've ever wanted. Okay, but let's actually see now, well, how does it work? Can we implement it and does it work? So I'm going to talk about the algorithms, right? How do we do this? So what we've got so far, right, our library has these operations. You could add way more, but this is already a really good starting point that allows you to implement a lot of interesting, non-trivial algorithms and see the benefits. So we have transform, aka map in our library, because I guess it was inspired by functional languages, but unfortunately C++ calls dictionary a map, so we can't call it that. So we've got transform, which is much more characters to type. We've got scan, which we've seen before, right? Those are just prefix sums with a fancy name. Of course, scan doesn't just have to do literally plus, right? You can give scan any operator. You can do a prefix maximum, minimum. You can do any fancy associative operator. Time permitting, I'll show you a really cool one at the end. Okay, we have flatten, also known as join in ranges. Ranges calls this join, but this is just you have nested ranges and you want to glue them into a single range. So like you have a vector of vectors and you just want one range, so it's not nested anymore. That's called join or flatten. I'm going to call it flatten because that's what it's called in our library. And of course, zip, right? Anyone who's used Python knows zip, right? It's a very nice, convenient little function where you can just iterate over multiple ranges in lockstep, right? So you have multiple ranges and you get to iterate over the first element of all of them, and the second element of all of them, and so on, right? So Python programmers, one of their favorite little abstractions, which is also in C++ ranges now. I forget if it was added in 20 or 23, but we have it now. We have it by now. And we also have terminal operations, which are, instead of taking a range and producing another range, which are what the top ones do, these take a range and just give you a value or something that isn't, there isn't another adapter, right? So you either can do a reduce, which just folds you down to one value, or toSequence, which is essentially to materialize it into, like, you're actually going to write the answer now. It's not lazy anymore. You're just going to write out the answer, okay? So what is the typical pattern, right? How do we implement these things? Well, we said this is our sort of typical, framework for parallel algorithm here, doing some local pass, some global aggregation, and then another local pass. So we said that our goal is to add some laziness, but we already sort of established it's not possible to do everything lazily. Like, we can't be completely lazy because for like a scan or a filter, you need to know some information about what came before you. But we also don't want to just write out all the answers and be done with it because there's no laziness. So our key idea, the big idea here, is we are going to be a little bit lazy. We're going to do some work up front, okay? Unlike std ranges views, which do no work up front, they are required by contract to be constant time. We're going to do some work up front and then defer the rest lazily. And we're going to put the split here. So we're going to do this like first local pass immediately, as well as whatever like global aggregate information we need, because that global information is what each block needs to know its values, right? And we'll do the second part lazily. Okay, so instead of being completely lazy, we're being a little bit lazy. It's like, you wake up, you're feeling tired, you're like, I don't want to do all my work today, but instead of doing none, I'll do some of it. And I'll do the rest later. So we're doing that, right? We're just being somewhat lazy. We're getting a head start and deferring the rest. So the typical pattern will look something like this, right? Our adapter's constructor, right? It will go and process the blocks in parallel. It'll compute whatever per block metadata it needs, like the block sums for scan. Then it'll aggregate those, and it will then remember the aggregate. So it will store those in the adapter. Okay, so it will store something. Again, it's not completely lazy, just somewhat lazy. We're still going to store a little bit of data. But notice that the key here is that we're only storing a little bit of data instead of storing the entire answers. So we're going to use much less memory and therefore save bandwidth, right? That's the punchline coming up. And then when we iterate the range, right? Well, when we get the iterator beginning to a block, it's going to look up the metadata for the corresponding block. It's going to remember that in the iterator. And then as you iterate, now you compute lazily within each block, right? So the key here is each block is still computed completely lazily on demand. We just need some pre-processing just to give the blocks the starting information they need to begin that process, okay? And so, for a technicality, this does mean, right, that because our constructor does usually linear work, it has to read the sequence. This does mean that it's not constant time to create one of these, which means technically, according to the C+ standard, this is not a view. So I unfortunately cannot call these views, right? They don't satisfy the definition of view. But they are going to be, they're going to do exactly what we want. They're going to be super useful. Just can't call them views. So let's see some examples, right? So block iterable transform, aka map. This is actually the simplest one. So this is actually one that doesn't actually need to take full advantage of the block structure, right? So the state for a transform, right? We have some range. It just needs to remember that transformation function, right? The function you're applying over every element. And so all we need to do is actually store the function. So map is kind of this simple one where it doesn't actually need that two-pass algorithm. It actually only needs one pass. So this one actually can be completely lazy. This one does not need to pre-compute any metadata for the blocks. Right, so this one actually is technically a view, right? It's the one that is a view technically. And so iterating this just, iterates through each block in parallel and applies the function to the element in the range, okay? So this is one of the few that actually preserves random access, right? If you give transform a random access range, you get back a random access range, right? Which is not the case for most views, which tend to give you back forward ranges. So this is one of the few that actually works and preserves random access, which, this is already in the standard library, right? Like stdranges has a transform view which takes a random access range and gives you back a random access range. Okay, so that's the simple one. Let's see the non-simple one. So let's look at scan, right? Our favorite parallel algorithm. So we have our input, our blocks. Now, what do we need to store in the adapter? Well, for each block, right, to be able to iterate and compute the scan, each block, remember, it needs to know its starting value, right? That's what our parallel scan algorithm computed before. So we're going to have to compute that when we construct the adapter, right? So we're going to compute the block totals, just like we did with the parallel scan, and then do the prefix sums, and then pause there, right? That's the construction. So, think of it as we are just doing like half the algorithm. We're doing half the scan algorithm now, and then we're deferring half the algorithm to be lazy and going to do it later as we iterate the range, right? So that's giving us our middle ground, right? Our best of both worlds, where we have to do some computation up front, but we get to defer a bunch of it to later, where we can be lazy and therefore save a lot of memory. Right, so once we go to actually iterate the range, right, when we grab the beginning of a block, right, we get our block start value from the prefix sums, and then iterating the range, right, now it just looks like a sequential scan, right? You have your starting value, your start value for the block, and every time you increment the iterator, you add the next value onto the prefix sum, okay? So it's just our parallel scan algorithm we saw before, but we're just cutting it off and saying, look, just do the first part of the algorithm now, save the rest of the algorithm to be lazy, right? So we do some work up front and we do some work lazily. That is our middle ground that gets us our best of both worlds, okay? Pretty cool. All right. So we can keep going with ideas like this, okay? So we can do flatten as well, right? AKA join. This one's a little harder to wrap your head around, especially in the picture, because remember, flatten takes as input a range of ranges. And remember that a block iterable range is a range you can split into blocks. So we now not just have a range of ranges, we have blocks of ranges of ranges. So we have 3 levels of nesting here. So this one, writing the code for this was kind of painful to remember which of those 3 levels you're currently iterating through. But we don't have to write the code today. We're just going to do it with pictures. So pictures are much easier to understand than the actual code. Feel free to look at my code if you want and flame me for it. But we take as our input, right, a range of ranges, which are themselves split into blocks. So to do a flatten, right, what we need to understand, right, what we want is essentially just an iterator. At the end of the day, we want an iterator that will iterate through all of those inner ranges as if they were one range. So our state essentially needs to be a pair of iterators here. We need an iterator to the current element in the inner range that we're looking at. But once that iterator hits the end of the current inner range, it then needs to know what the next one is. So it needs to jump up to the outer range and increment that iterator to jump over to the next range in the sequence. Okay, so our state essentially needs to be, for each block, we need to know not just one iterator, but a pair of iterators, right? What's the current inner element we're looking at, and which of the ranges is it in? So that when we hit the end, we can jump over to the next one. So our whole pre-computation algorithm essentially has to compute where those are. Okay, where are those positions? Which iterators are those? And what makes it challenging, remember what I said before, is that for these algorithms to be composable, blocks must always be the same size. So the output of this algorithm needs to be something that gives us blocks of the size we want. So the goal here is essentially just to find checkpoints within this nested sequence of evenly spaced elements. So in my actual library, right, blocks need to be pretty big, right? Because you need pretty big blocks to make the overhead of parallelism worth it. So in the actual library, blocks tend to be 2,000 size. On my slides, they're going to be 5, because we can draw that on the slide. So you imagine conceptually what we want is to essentially find iterators to every 5th element in these input sequences, right? So given this nested range of ranges, we want to essentially locate every 5th element. That is the challenge, okay? So to do that, right, well, we need to know the sizes of the ranges. So we're going to compute the sizes of the ranges, which we can actually do, by the way. That's actually a transform, right? That's a transform from the range to std_range's size of that range. So we can already start to reuse some of our previous algorithms in here. And now, similar to scan, we do prefix sums again, because we need to know, essentially, for each range, right, how many elements come before it. Because if we're trying to locate, say, every fifth element, well, I want to know how many elements came before me. If it's a multiple of 5, I am one of them, right? I am one of the every fifth elements. So then we essentially just take those prefix sums and we try to find, every fifth element. And you can do that different ways to do it. One way is to binary search on the prefix sums, okay? So you can binary search to try and find every fifth element. If you don't like binary search, you can also do it essentially by linear searching, just left to right over the outer ranges, right? Just searching over those, keeping track of the number of elements you've seen so far. Every fifth one, you write it down, right? You save it in the adapter so that you know where your block starting values are, right? So you can compute those, right? You find those either by binary search or by left to right, just searching, pulling out iterators to every fifth element. Okay, so it's effectively a load balancing problem, right? You're given a whole bunch of not evenly sized things and you want to pretend they were evenly sized. You want to find every fifth one so you can break it into evenly sized things. That's a classic load balancing style problem. Okay, now once you've found all these iterators, that's the final part of constructing, right? That's the non-lazy part. That's what we do up front. Now, this is still memory efficient, right? Because remember, of course, on my slides, their blocks are size 5, but in the real library, right, blocks are thousands of elements. So the actual size of your adapter is very small relative to the range, right? If your range has n things, you need n divided by 2,000 iterators. So the amount of space you need for this is very small. And remember, that's what we were trying to do in the first place, is we were trying to save on wasted temporary memory. So, we've basically gone from needing n memory to n divided by 2,000 memory, right? So that's pretty good saving. That's 99.95% memory savings. Okay, so that's our adapter state. And then our iterator, as I said, right, once we've actually constructed this and we want to iterate over it, our iterator just contains 2 iterators, right? It knows the inner iterator of the element it's currently looking at, and to advance it, right, when you hit the end of one of those inner ranges, you look at the outer one so you can jump to the next one, right? You know to jump to the next range that you're concatenated with, okay? So you just look up those starting iterators that are stored in the adapter and use those to iterate through, okay? And that's our flatten algorithm. And this, I want to point out how useful this is going to be. We'll see on the next algorithm why this is particularly useful. But what this algorithm is essentially doing is taking a bunch of unevenly sized things, right, these inner ranges, and converting it into a bunch of things of the same size, right? It's trying to load balance them into equally sized blocks, okay? And this is going to turn out to be really useful because by definition, our block iterable algorithms to work need equally sized blocks. So this algorithm is going to be super useful for taking non-evenly sized blocks and making them evenly sized, right? So this algorithm is going to be useful not just for its own purpose, but for building other algorithms. And I'm going to show you that now with filter, okay? So you could imagine in your head, okay, a parallel algorithm for filter. I look at all the blocks, I count how many algorithms survive the predicate, I mark which ones survive the predicate. Then I'm going to have to do prefix sums and search for where, the 5th survivor is, the 10th one to do the load balancing. But hang on, that sounds like it's going to pretty much do the same steps that filter had to do, right, to find every 5th element. So instead of actually writing all that code again, which is 90% of the code for this would be duplicating the same code as filter. Why do we have to make it, why does filter have to be a first-class adapter? Let's use Flatten to implement filter. And I want to point this out because it's a really cool trick that once you have just a few of these adapter algorithms, you can implement tons of them by composing the ones you've already got. You don't have to write very many of these from scratch. Once you've got a handful, you start to realize that all the other ones you wish you had are just compositions of the ones you do have. right? And I want to demonstrate that here because you might say, well, isn't this marginally less efficient? Like, yeah, maybe it's wasting one extra iterator, so it's like going to be like a 1% slower, maybe. But I want to demonstrate this idea that you can save on rewriting everything from scratch. As soon as you've got a handful of these things, you can start to compose them and build so many more things. Okay, so the way our filter works, right, is you have your blocks. Within each block, you go through and you find the survivors, right, the elements that satisfy the predicate. You now remember where they are. So in my case, I save iterators to them. So I just save the iterators pointing to the survivors. Now, in terms of memory efficiency, this is good if not too many elements survive. If every element survives, okay, then this is basically the same memory efficiency as if you just did a regular filter. So this is good, right? I mean, in the worst case, it's no worse than the previous algorithm. But in the best case, you save a lot of memory because you only have to use memory proportional to the things that survived here instead of a temporary memory that would be the same size. So all we can do then is just take our survivor blocks and flatten them, right? Because now what we essentially have are blocks of survivors. Well, that's just a range of ranges, right? So I can just flatten them out. And notice that what flatten is doing is it's doing that load balancing. It's doing that thing where I said, look, blocks must always be the same size. For these to be composable, blocks have to be the same size. So filter can't just take in a bunch of blocks and then output the filtered blocks because the blocks are now smaller, having had things filtered out of them. So the flatten is what comes along and reload balances them and makes the blocks the same exact size again, right? So this is really cool, right? We save on repetitive, redundant code, and we get our algorithm in a few lines of code, essentially. And technically, since we're storing iterators here, right, to make this work, of course, I don't want my user to call filter expecting, they put in a range of ints, they expect a range of ints back, somehow they get a range of iterators to int. I need to dereference them for the user. We have that. That's a transform, right? We can just pipe this into a transform that dereferences for the user. So we've built our filter adapter. It's just a composition of a flatten and a transform, right? The transform just gives it that lambda which says, look, take the iterator and dereference it for the user. So the user puts in a range of ints, they get back a range of ints, they are happy. Everything works just like they want. So I want to emphasize how useful this is, right? We're not just implementing all of these from scratch. Once you have a few of these, I mean, we only implemented 3 so far, and that was already enough to get a 4th one just by composing the ones we already had, right? We didn't have to write them all from scratch. We just did a little pre-processing and then composed existing adapters that we'd already written. And so once you have these views, right? Sorry, they're not views, that's illegal, right? They're not constant time. Once you've got these range adapters, non-constant time range adapters, you can start to compose them and get new ones. And you can really start to build up a nice library of these algorithms. Okay, so that's how they work under the hood. Last thing we want to talk about, of course, do they work, right? What can we do with them? Are they actually useful? And do they make my code faster? The answer is going to be yes and yes as a spoiler, but let's prove it. So here's a cool example, right? I teach algorithms, so we're going to do some algorithms examples. So let's do a breadth first search in parallel. So we're given a graph. If you don't remember what a breadth first search is, we're given a graph, and we want to label each vertex with its distance from S. And the way this works is we essentially just compute vertices in sets of what are called the frontier. Frontier is just the current set of vertices at the current distance we're looking at. So the initial frontier is just S, distance 0. The next frontier is everything at distance 1. The next frontier is distance 2, distance 3, distance 4, and so on. So what we're going to do is we are going to compute frontiers one by one. That part will be sequential, right? I don't think you can make this completely parallel, right? I don't think that's possible. So our algorithm will, be still sequentially by the diameter of the graph, but we're going to put all the parallelism in the computation of each frontier. So we're going to still get plenty of parallelism. Okay? So how do we do that? Well, we have a frontier, right? We have the current frontier. We're going to say each vertex has an atomic label, right? We're going to need to use the atomic. This is the one tiny bit of concurrency in this talk, is we're going to have our label be an atomic. Okay? So the goal here now is to go from the previous frontier to the next frontier, using as much parallelism as possible. So how do I do that? Well, I start with my previous frontier. I need to know all the neighbors right? Every vertex in the current frontier, I need all the neighbors because they're the candidates to be in the next frontier. Because all my neighbors are either the next frontier or they're from a previous one and I want to ignore them. Okay, so we can do that. That's a transform, right? Just transform from a vertex to its list of neighbors. Okay, so we take in a vertex, we return the list of neighbors of that vertex. Okay, but now this is not a range of vertices. It's a range of ranges of vertices, right? Because each vertex yields us its neighbors. So we want to flatten this. We have flatten. Let's do it, right? We have flatten. So we take our list of vertices and we flatten it out. So now we have all of the adjacent vertices to this frontier, but possibly with two problems. One, we may have vertices that already we've seen before. They may be from a previous frontier. We don't want them. We also may have duplicates, right? Notice that several of our edges can point into the same vertex. So we want to make sure we get rid of duplicates or we would quickly blow up and this could be exponential time if you keep duplicates in. So we want to get rid of duplicates and get rid of anything that already has a label. And that's the reason we have this atomic, is we can kill two birds with one operation. We can just do, this is the clever part, we can just do a filter here. I'm going to filter my candidate vertices. The criteria is that I successfully write the distance with a compare exchange. So if that vertex was in a previous frontier, this compare exchange just definitely fails because it wasn't an unwritten. So I'm just using -1 to mean like not labeled. We haven't seen it yet. So if the vertex was previously labeled, the compare exchange definitely fails. If it's a duplicate, if multiple vertices are adjacent to the same one, only the first one that succeeds will return true and survive the filter. So this will get rid of all the duplicates. So we've killed two birds with one range adapter, right? We've gotten rid of the duplicates and we have gotten rid of anything that's already been visited. And then we can just like turn this into an actual sequence, right? We can stop being lazy and say, cool, here's the next frontier. So algorithm's kind of cool, kind of clever, but what I want you to focus on, right? The most important thing, this isn't an algorithms class, right? You're not in my algorithms class right now. You don't need to understand it completely, but what I want you to take notice of, this is just a composition of those lazy range adapters that we just wrote, right? This is just a transform piped into a flatten, piped into a filter, and into a terminal operation. So we can do this using our library that we just talked about, that we just wrote. So we implement this, and of course, we're going to measure, did it work? Okay, we're going to measure the performance. We're going to do some benchmarks, because otherwise you won't believe me whether it's fast. So let's compare, what would the materialized version be? So if I actually just wrote the intermediate range at every step rather than being lazy, well, since we've got all of these steps, right, we would essentially take about 4 writes per vertex, right? Like we'd use 4n memory for n vertices in the frontier right now, okay? 4 per vertex, that's kind of a lot, right? But when we're lazy, okay, we're still doing multiple reads, but the key thing is, remember, by being lazy, most of the intermediate writes get fused away, right? Most of those writes are going to be fused away. And if you go through and look at the algorithm, you can essentially see that we're going to fuse away half of the writes, right? So the filter is still going to keep writing, it has to, but essentially the transform, right, and the flatten no longer have to do their temporary writes. So 2 of the 4 stages of the pipeline get completely fused away and get rid of their temporary writes. So we're doing basically half as many writes. We're using half as much memory here. So if we're right about our hypothesis at the beginning that memory bandwidth is going to be our bottleneck and we're now using half as much memory, probably predict about twice as good scalability, right, if I'm right. So let's look at the graph and yeah, that's about 2, right? It's about twice as good of a speed up because we have gotten rid of half the wasted memory, right? Half the memory is gone, half the bandwidth wastage is gone, so we get about 2 times better scalability, right? So this is both, showing you that the block lazy trick works, also showing you that our hypothesis that memory was the culprit is still right, right? Because we're still doing about the same amount of compute in both cases. We're just not saving the results to wasted temporary memory. Okay, cool. Okay, well now we've got one more application then we'll wrap it up. So parallel integer addition, this is cool. So let's say you have two very big integers, right? Millions, hundreds of millions of digits. So you can't represent them in an int, right? So you're going to use some kind of big int representation. On my slides, I'm going to use base 10 because we're going to understand that the best as humans. But of course, in actual code, don't use base 10. You will use a bigger base that actually uses all your bits. So if you store each digit as a character, you might use base 128, for example. But as humans, the example is going to be base 10. So how does this algorithm work? Well, we know how to add numbers from grade school, right? Like we know how to do this, except maybe we don't quite know how to parallelize it. But we know that we can at least try and figure out the idea. We know we can pairwise add all the digits. Okay, not quite done though, because there's no 10 digit in base 10, right? Or an 11 digit. So some of the digits are going to go too big. Those digits have to cause carries, right? They have to increase the digit next to them. So there are two ways you can carry. If the digit before you was too big, if it went over 9, you get a carry. Okay, that's the easy one. But then notice that also the 8, right, the second biggest digit, also got a carry, even though the guy before it wasn't too big. That's because the guy before it and the guy before it got a carry. And when you carry over a 9, it propagates. We call this carry propagation, right? Like if you do 9999999 and you add 1, what happens? The carry jumps all the way over, right? The carry propagates, goes like this. Jump, 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 wee, there it is. So carries jump over consecutive 9s. So that's the tricky part about parallelizing this algorithm, right? Is figuring out how to do that propagation. Because sequentially, easy, that's a loop. But how do you do that propagation efficiently in parallel? Right? So once you've got your carries, now you just add, right, your carries to your original value, right? And mod 10 so that you don't have digits that are fake. Okay? So that's the algorithm. How do we parallelize it? Now, I don't expect you to understand there's some clever math that goes on here. Again, I'm not concerned about, teaching you the clever math, but what I want you to see is what the algorithm is doing, right? What tools is it using? So we're going to start by doing those pairwise additions. Now, I said before, we can define new adapters by composing our existing ones. A really nice, convenient one is called zip width, right? So zip width just essentially does a zip and then applies the given function to the zipped elements, right? So in this case, literally pairwise adding. I'm saying zip up A and B and add the corresponding elements, right? So, the nerd version is zip width is essentially a composition of zip, transform, and then apply to actually explode the tuple into the parameters of the function, right? Yeah, just think of zip width. It's just composing zip and transform, right? I'm applying this function to the zipped up tuples in my range, okay? So that's the pairwise addition. Now, the really wild, clever part, how do we do the carry propagating part? How do I figure out, okay, the guy before me was bigger than 9, that's easy. But how do I know if the guy before me were all 9s, if there was a streak of 9s, and then there was a carry before that? There is a clever algorithm for this. Again, don't worry about the math, but it turns out the punchline is this is an associative operation you can scan over. Essentially, the operation is just check the previous thing, right? Check, okay, is it a 9? If it's a 9, take what came before it, because I want to see if there was a carry that jumped over some 9s. If it's not a 9, just take the current value. Okay? So again, don't worry if the math is a bit kind of what, because this is magic when you first see it. But essentially, right, this is a clever bit of math that essentially propagates those carries. It says if there's a 9, take the thing before it, right? Jump over. Otherwise, just take whatever's there. That's the carry propagation algorithm there, and it's just a scan. And finally, our result, we just do another pairwise add, right? We just, again, pairwise add our sums and the carries, right? So again, we can hit that with a little zip width where we just add the sum to the carry and output the result. So again, the math is kind of complicated. I don't care if you want to understand the math. You can ask me about it later if you do. But again, what's the punchline here? This is just a composition of our range adapters, zip, scan, zip, right? That's it. It's just a composition of these algorithms. So we can do it and implement it, and it will automatically fuse and be faster. So again, similar to the last time, right? If we were to do this writing out the intermediate values, we would essentially do 3 writes per digit. We'd have to write out the 3 stages of the pipeline. But if we do it lazily, all the intermediate writes, they're gone. They're fused away. So we only need to basically write one result per digit. We just write the answer. Those intermediate zips and scans, gone. They're not written to memory. So we do like a third as many memory writes. We use a third as much memory. So we expect 3 times better scalability. And what do you know? 3 times better scalability. I'm not lying to you, right? This is really everything, right? If you reduce the amount of memory, you reduce the memory bandwidth by 3, you get 3 times better scalability. I said bandwidth is everything, right? If you take one message home from this talk, right, it's that bandwidth is everything. It matters so much for scalability. So that's the end of the examples. If you want to check out, I do have an implementation of this. You can check it out on GitHub. As a disclaimer, I haven't actually implemented the pipe overload thing. So you don't get that nice, cool syntax. You actually just have to chain function calls because, yeah, I didn't have time to implement the overloaded pipe operator. So that will actually be easier with C++20 because I wrote this with C++17. So we could add the overloaded pipe operator and have the cool syntax, but the algorithms are all there. You can have a look, as well as the documentation. That's the second link. So, all right, amazing. What did we learn today? So take-home messages here. Well, bandwidth matters, right? Again, if there's like one message you take home from this, if you didn't quite understand some of the algorithms, the math, just a worthwhile message that you can take home from this talk is that bandwidth matters, right? It is the bottleneck for most parallel algorithms. But lazy evaluation comes to the rescue. It saves memory by fusing adjacent operations, so we don't have to store intermediate wasted stuff. But unfortunately, parallelism and lazy evaluation kind of don't work together, so we had to invent block iterable ranges, this cool middle ground between random access and forward ranges that let us get the best of both worlds. And then finally, we can implement these algorithms, run them through some benchmarks and show that, hey, they really do give speed up, right? You halve the amount of wasted memory bandwidth, you double your speed up. It's just that cool. And that's everything we've got for today. Thank you very much.
Can I ask a question? Yes.
We'll take questions.
Yeah, thank you for the talk. I have a question about how you compose the laziness. For example, if you pipe a scan to another scan, so when you construct the second scan, when you need to compute some prefix sum, right? Mm-hmm. Then you have to materialize the previous scan.
Okay, so the question is, how do we compose the laziness, right? The example was if I do a scan of a scan, the second scan, surely, it has to compute the sums, which means it has to materialize the first scan, right? That's the question.
Yes.
So essentially, the key difference here is we don't have to materialize it. We do have to compute the first scan, but we don't write it down anywhere. We don't save it to memory. We just keep it in local memory as we loop over it. So remember, we're not trying to save compute. Yes, we are still doing that scan. We're still doing the compute. But we were never trying to save compute. We're trying to save memory. So we do the scan, but we don't write it down anywhere. We don't save the answer. And that's the key difference. That's why we save bandwidth and we get our better performance.
Effectively, you compute twice, right?
We compute twice, yes. That's more or less required for a lot of parallel algorithms, right? To compute twice because for scan to be able to parallelize and know, okay, what value am I here? I have to know the stuff before me. But the key is that we don't actually care about wasted compute. Computing twice, I'm totally okay with as long as I don't wastefully save the answers from the first one to memory. I'm doing more compute because that's okay because remember, we're bottlenecked not on compute. You saw how many wasted cores we had. We were bottlenecked on bandwidth. So I don't care about wasted compute because we're bottlenecked on bandwidth.
The pipeline is the wasted compute you have, right? If I have scan, then you have to compute n times for each element.
But you'd have to do that anyway if you did the non-lazy one, right? It's no worse. It's the same amount of compute as the non-lazy one, but you're saving memory. The headline is just same amount of compute, save memory. And that's a huge win when your bottleneck is bandwidth.
Cool, thanks. For the second question, the way you implemented the join view, you only store the iterators. Mm-hmm. But if the inner range is not a non-borrow range, then you got all the dangling iterators.
Good, yeah. So some detail, right, of my flatten or my join, right? What if the ranges are PR values? Yeah, so in my actual library, I have an overload for that. If it's PR values, then I materialize them because otherwise we're dangling. Yeah. So essentially, yeah, if you actually look at my actual library code, it has a lot of like selected overloads where it checks. If things are PR values, sometimes you do something different to avoid dangling. So yeah, the code I showed you was the non-PR value version. If it's PR values, you're completely right. You do have to do something slightly different to not dangle. So the actual code does do that, just not the slide code.
Thank you.
Cool.
Hey, thanks for the talk. I actually have some comments and a question. So first of all, the comment. This talk has almost zero intersection with my talk, so you're all welcome for
Brilliant.
range algorithms.
Excellent. That's good.
Yeah, that's good. The second comment is zip from the standard library also preserves random access. So we
That's
can
true. Yeah,
parallelize
zip is
with
all.
that.
Yeah, zip also preserves random access. That's true. I just didn't show the code for zip because it is
Yeah,
kind of boring,
but
right?
The point is you can use zip for a new API with parallel range algorithms today. I mean, not today when it's released as the C++26 with zip. There is no problem with that. The
Yeah.
question is, maybe I missed that. How do you determine the block size, or is it like controlled by the user?
How do we determine the block size? The answer to that is really boring. In my library, it's hard-coded. It's 2000.
I see. So it's
It
just,
is a
some
constant.
heuristics.
It's just a constant right now, yeah.
okay.
You could make the user choose it as well, but for simplicity, I didn't.
Okay.
And I have to
then
get off the stage.
For
We can keep talking later, but I have to get off the stage. I'm being
Okay,
told
sure.
that